Hi everyone, I'm happy to present our work, Labit, Latent Audio Visual Vision Transformers for speaker verification. This will be the outline of my talk. First, I will briefly presenting what is audio visual speaker verification. Then I will present the motivation behind the proposed approach and I'll present the proposed approach, followed by some of the experimental results that we achieved with this method. And finally, I'll conclude this work. Speaker verification using audio-visual fusion has been recently gaining a lot of attention as they can offer complementary relationship which can be beneficial to outperform unimodal approaches. And this is a very high-level block diagram of audio-visual speaker verification, where given the video stream, we pre-process the audio and visual streams. We do cropping and alignment on facial images to extract the cropped and aligned faces. And then we extract the audio stream and feed that to visual and audio backbones to obtain the feature representations of each of these modalities. And then we feed these feature representations to the fusion module. And finally, we use this final audio visual feature representations to verify the speaker. Most of the existing approaches rely on sophisticated attention models to effectively capture both intra and intermodal relationships across the modalities. However, these state-of-the-art models, even based on transformers, involves quadratic computational complexity within the self-attention and cross-attention modules. Um, most existing state-of-the-art models, moreover, they rely specific modality-specific architectures for both audio and visual modalities. So in this work, we have explored the prospect of adapting the large pre-trained models, which have been trained on images, to the context of audio-visual learning while maintaining low computational complexity so that it can be feasible with small-scale environments. So this is the very high-level block diagram of the proposed approach. So we feed the visual and audio modality. So here we extract the spectrogram of the respective audio segment, and then we feed the facial image and spectrogram of the audio segment to parallel VAT architectures. So we share the pre-trained weights across the two VAT architectures for both audio and visual modalities. And we introduced these Lavit adapters in each of these VAT layers for both audio and visual modalities. So we will see in more detail what is this, what are these Lavit adapters. So as we can see here, in these Lavit adapters, there are two major blocks. One is latent self-attention module, and the other one is cross-modal attention. So the main objective of this Lavit adapters is to reduce the computational complexity involved in the cross-modal attention. So in order to do that, we compress the tokens of audio and visual modalities. So for instance, as we look at the left side audio to visual Lavit adapter, we introduce latent tokens, which are learnable parameters. And we use these latent tokens to compress the original audio token. So for instance, in swing transformers, we have 2000 tokens. So by using these latent tokens, which can be around 10 tokens, we are able to compress 2000 tokens of this audio modality, of the spectrogram of the audio modality to 10 tokens. And we feed that 10 tokens to the cross-modal attention, which is used to compute cross-attention across the modalities, where we compute cross-attention across the compressed tokens of audio modality and the original tokens of visual modality. So by computing the cross-model attention across the compressed tokens and the original visual tokens, we can see that the quadratic computational cost involved in the cross-model attention is drastically reduced. And we do the same thing for visual to audio modality also. And we use different adapters for audio and visual modality, which means the latent tokens are not shared between audio and visual modalities. So we can see these Latent adapters in more detail. As I mentioned before, so we have these latent tokens, which we feed that along with the original tokens of each of these modalities. And then we feed that, we perform latent self-attention, which is basically, you can think of it as cross-attention across the latent tokens and the original tokens of each of these modalities. And then once we get the compressed tokens, we use the compressed tokens to compute the cross attention across the modalities. So these are the equations that are associated with this cross-modal attention and latent self-attention module. And this is how we integrate these Latent adapters into VAT layer, like at each layer, at every layer of the VAT architecture. So we integrate two Lavit adapters, one for the self-attention module and one for the MLP module, feed-forward module. Um, Basically, we feed the input to the self-attention module and the Lavit adapter. And as I mentioned before, that we freeze the pre-trained weights of the original VAT architecture. So the weights involved with multi-head self-attention and feed-forward network are frozen. And we compute the features, and then we also feed the input to the Lavit adapters, and then we add the output of the Lavit adapters with the output of original VAT layer, as we can see in these equations. And same with feed-forward network also. We feed the output of self-attention module to both Lavit adapter and feed-forward network. And finally, we add the outputs of both Lavit adapter and feed-forward network. And this is the experimental setup. So the proposed approach has been evaluated on WorksLab one dataset, which has 1,211 speakers, which consists of 1,48,642 utterances. And the models are trained using the WorksLab one development set of 1,150 speakers and tested on WorksLab one more set of 61 speakers. And the proposed fusion model is compared with some of the widely used fusion strategies as well as some of the state-of-the-art models to evaluate its performance. So this is the ablation study that we did to understand the performance of the model, to understand the impact of this latent token. So what we did, we conducted a series of experiments across four variants of VAT architectures with latent tokens and without latent tokens. So the difference here is in the set of experiments where we used latent tokens is the original Levitt adapter that we have seen before. And in another set of experiments where we didn't use these latent tokens is basically where we computed the cross attention across the original modalities. So that's the reason we can see that by introducing latent tokens, there is a slight increase in the number of tokens because we are introducing the latent tokens through these Lavit adapters. However, when we look at the performance of computational complexity in terms of G-flops, we can see that with latent tokens, we are able to reduce the computations involved in the cross-attention modules. And especially we can see that the uh, uh, we can see that for swing transformers, it is we are able to drastically reduce the computations involved. As we can see that the G flops has been drastically reduced for swing transformer architectures. And we can also see that using latent tokens, we are able to achieve better performance than the case where we don't use the latent tokens. And this can be attributed to the fact that using latent tokens, it also helps to compress the tokens in a more representative way, so that it is able to efficiently represent the tokens of each modality. And these are the results in comparison to some of the state-of-the-art models. As we can see here, that we are able to achieve the best performance by comparing to some of the state-of-the-art models. So here, the three models that we have shown here, joint cross-attention, dynamic cross-attention, and recursive joint cross-attention, or cross-attention based models, where they have used sophisticated cross-attention models using joint feature representations. Um, and but the problem with these models is they are computationally very expensive, and it is very difficult to use these models on large scale data sets. But if we see, as we can see that our model is computationally less expensive, and it is also scalable, that we can extend this, we can train these models even with large scale data sets. So we have shown that by introducing latent tokens in the Latent adapters, we are able to achieve good performance using V8 architectures while maintaining low computational complexity. And by employing the same V8 architecture with the shared pre-trained weights, we also circumvent the need for modality-specific architecture. So we don't need separate modality-specific architectures. We use the same architecture with shared pre-trained weights that drastically reduces the need to separately train audio and visual models. And the latent tokens in Latent adapters, they help to drastically reduce the original number of tokens, thereby minimizing the quadratic computational cost of cross-attention. And we have shown using by conducting extensive experiments and oscillable data set that the proposed model is able to achieve a very good performance, and it is a promising line of research. Thank you so much.